Hello everyone, I'm J Wildberger. Let's have a look at an example of row reduction. This is also sometimes called Gaussian elimination. Okay, there's two terms for it, and it is a fundamental algorithm that sort of pervades many aspects of linear algebra. It gives us a concrete technology for solving systems of linear equations when they can be solved, finding out if there are any solutions, and if so, how many solutions there are, and perhaps parameterizing the solutions. So it's a very flexible and powerful thing. The history of row reduction, well, it actually is usually attributed in modern times to Gauss. Carl Friedrich Gauss was a great German mathematician who lived around the 1800s. But actually, it goes back much earlier. It goes back to ancient Chinese mathematics. There was a famous Chinese text written or compiled somewhere between 200 BC and 200 AD called 9 Chapters of the Mathematical Arts. 9 Chapters of the Mathematical Arts. And in that work, the technique of row reduction was laid out for the first time. Okay, so what I want to do is I want to illustrate what happened. So there's a general theory, but I want to show you first a concrete example so that we learn how to approach the problem in a very systematic kind of step-by-step procedure. Okay, so let's start with this system of linear equations. We have 3 equations in 3 unknowns. The variables are x1, x2, and x3. So we know that one interpretation of this problem is that we have 3 planes. Each equation represents a plane in 3-dimensional space. And at this point, we don't know what the various relationships are between these planes. We don't know whether the common intersection is a point, or maybe a line, or maybe even a plane. So that's one of the things we want to find out. Another interpretation that we've seen is that we can also think about this system as representing a relation between vectors. So if you actually sort of look at the columns of what's happening here, we could also write this in an alternate form as x1 times the vector 2, 1, minus 1, plus x2 times the vector 7, 2, 4, plus x3 times the vector 4 minus 1, 13, equals, squeeze it in here, 2, 1, 1. Get sort of an alternate form of the same system. Okay, now what we're going to do is we're going to work uniformly with a matrix approach. Okay, so with a matrix approach, we're interested in the matrix of coefficients and an augmented matrix. So I'm going to write down the matrix equation first. So the matrix equation is in terms of a 3 by 3 matrix, 2, 7, 4, 1, 2, minus 1, minus 1, 4, 13. Also in terms of a vector of variables, x1, x2, x3, equals, on the right-hand side, our vector of coefficients, 2, 1, minus 1. That's a minus 1 there. Okay, so that's now in the form that we often write ax equals b kind of form, which is quite attractive. Now, to actually do the row reduction, to simplify this, what we're going to do is we're going to work with the augmented matrix. So we think this thing has augmented matrix. Okay, what is that? It's when we put the A matrix together with the B column separated by a line. So 2, 7, 4, 1, 2, minus 1, minus 1, 4, 13. Then a line, and then on the other side of that line, 2, 1, and minus 1. So that has all the information, the numerical information of the system of equations. And any one of the original equations can be just sort of read off by reading across one of these rows of this augmented matrix. For example, the second row would tell us that x1 plus 2x2 minus x3 equals 1, which is the same one as that one there. Okay, so what are we going to do? We are going to row reduce this thing. We're going to perform elementary row operations. So at each stage, we're performing one of the 3 elementary row operations, which replaces the given system of 3 equations with 3 other equations which are equivalent. Equivalent in the sense that the solutions are exactly the same. Okay? All right, so we're going to just create a series of steps, and the steps will be indicated with arrows. So we're going to move from one augmented matrix to another, to another, to another, hopefully moving towards a simpler and simpler form. Okay? Eventually, the form of the augmented matrix will be so simple that we'll be able to read off what the solutions are pretty easily. That's the aim. Okay, so what we're going to do in this case is we're going to switch 2 rows. We're going to switch row 1 and row 2. That's easy to do. So I get 1, 2, minus 1, 1, 2, 7, 4, 2, and minus 1, 4, 13, minus 1. Why am I doing that? I'm doing that so that this 1 that's there ends up at the top of its column. We like to have 1s at the top of the column. Why? Because we're going to use that entry to reduce the other entries in that column to 0. Namely, this 2 that's sitting there and this minus 1 that's sitting there. We want to replace those things with 0. We want to add multiples of the first row to both the second row and the third row to make those entries 0. Now, we could do that individually, but since you are all very smart, we're going to do this all at the same time. So we're going to do 2 operations sort of at the same time. The first operation is going to be aiming at getting rid of that 2. So I'm going to replace row 2 with row 2 minus 2 times row 1. And then in the same breath, same step, I'm going to replace row 3 with row 3 plus row 1. So I'm going to do 2 of those things. So let's see what we get. So first of all, the first row is not changing. It's where it is. Now, the next step is we're going to replace row 2 with row 2 minus 2 row 1. Okay, so we have to make this computation. 2, 7, 4, 2, that row, minus 2 times the row 1, 2, minus 1, 1. Okay, so what are we going to get? The 2 minus 2 times 1 is 0. 7 minus 2 times 2 is 3. 4 minus 2 times minus 1 is the same as 4 plus 2, which is 6. And 2 minus 2 times 1 is 0. So we have to do a little bit of arithmetic in our heads. All right, please do not use a calculator or reach for your calculator. You want to do this in your head. Okay, but you want to do it sort of slowly and steadily to make sure that you've done it right. Because if you mess up, especially near the beginning, well, everything is going to be messed up. Okay, so let's just check. 2 minus 2 times 1 is 0. 7 minus 2 times 2 is 3, yes. 4 minus 2 times minus 1 is 6. 2 minus 2 times 1 is 0. Okay, that row is right. Now, what about row 3? We were saying that row 3 is going to be replaced with the sum of the original row 3 and row 1. So we're doing it that way so that we get a 0 here. That's the aim. Minus 1 plus 1 is 0. 4 plus 2 is 6. 13 plus minus 1 is 12. And minus 1 plus 1 is 0. Okay, great. Now, at this stage, we're happy with column 1. Column 1 has been arranged just the way we want. It has a 1 up at the top, and below that 1, there's only zeros. That's excellent. Now we're going to shift our attention to the lower part. Okay, I'll draw it in here in red. So we're now going to switch our attention more or less to this smaller submatrix. if we just had that, we would say, oh, that's a system of 2 equations in 2 unknowns. So in some sense, we're starting with 3 equations and 3 unknowns. After having performed this first series of steps, we now more or less in the situation of having 2 equations in 2 unknowns. Okay, so we're going to sort of apply the same kind of thing, sort of just looking now at this smaller sort of submatrix. Okay, what are we going to do to this thing? Well, maybe I'll do a little bit of cleaning up. I'm going to replace row 2 with 1/3 of row 2, right? This is a common factor of 3. I'm allowed to multiply all the elements in a row by a constant. So I can multiply by 1/3. That will simplify that row. And similarly, once I look at it, I see that row 3 has this common factor of 6. And I might as well replace row 3 with 1/6 row 3. Okay. What happens when I do that? I get 1, 2, minus 1, 1. That's not going to change. And then this is going to be 0, 1, 2, 0. And this one's also going to be 0, 1, 2, 0. So it's a lot simpler now. That's quite nice. And moreover, we have the happy situation that we have a 1 here in this place, just like we ended up having a 1 up in that previous line. Okay? And we can then use this 1 to eliminate everything below it, namely that 1 that's sitting underneath it. Okay. So let's go over here. Okay. So I'm now going to take a new row 3. The new row 3 is going to be the current row 3 minus the current row 2. So the first row does not change. The second row does not change. What about the third row? Well, I'm taking the third row and I'm subtracting the second row. 0 minus 0 is 0. 1 minus 1 is 0. 2 minus 2 is 0. And 0 minus 0 is 0. Okay, now I'm in a pretty happy position because the leading entries of these rows, that is the leftmost sort of non-zero entry in the rows, are these ones right here. This third row doesn't have any non-zero entries, but the first 2 rows have these non-zero entries, which I've circled, and they happen to be 1, which is very nice, and they are staggered. So 1 at the top corner, and then we have to move right and down to get the next 1. So also those ones that I've circled have the property that there's nothing but zeros underneath them. Okay, so this is a pleasant kind of form for a matrix. We say this is in row echelon form. It's a kind of not an end result, but it's a kind of an island of safety. We've crossed this river and we've gotten to this island, okay, where we can pause and take stock. And this is sort of like the halfway point of the algorithm. I'm going to show you what happens further on. So you can see the entire algorithm expressed in this example. And then we'll go over it again. We'll sort of look more generally, more carefully at what the various steps that we're doing. But I want you to see it all in an example here. So after we have it in row echelon form, we are going to further row reduce. We're going to do some more row operations. And I'm going to now sort of start from the bottom up. So I'm going to circle this one twice. Okay, I'm going to think about it again. And I'm going to use it to get rid of everything above it. We've already got rid of everything below it. Now I'm going to get rid of everything above it. How am I going to do that? I'm going to replace row 1 with row 1 minus 2 times row 2. Okay, so what's the new row 1 going to be? So we're taking the row 1 and we're subtracting twice the second row. So that 1 will still be 1 because it's 1 minus 2 times 0. That's 1. The 2 minus 2 times 1, that's going to be 0. The next one, minus 1 minus 2 times 2. So that's like minus 1, minus 4. So that's going to be a total of minus 5. And on the right-hand side, we still put that bar. On the right-hand side, we have 1 minus 2 times 0. That's still 1. And we're not doing anything to this second row, so we'll just copy it. And we're not doing anything to the third row. We'll just copy that. Now we have graduated to almost a final form, really. So we've got the 2 leading entries, and everything else in the columns of those leading entries, which means things both below the entries and above the entries, are completely free of anything other than zeros. So those leading entries are the only things in those columns. These 2 columns that have these special sort of ones in them, just by themselves, these are called leading columns. So that's good. That's one of the properties of this, what's sometimes called fully reduced row echelon form. The leading entries are 1s. The other entries in the columns of those leading entries are all 0. And we have a row of zeros at the bottom. There's the row of zeros. It's just at the bottom. That's really not doing much for us. Now, this is a very happy situation. We've reduced the original system. Okay, we start off with this system of equations up here. We formed an augmented matrix for it right here. That was a rather complicated looking thing. Okay, and then we've row reduced it, and now we have this much simpler form, which is, however, equivalent to it. What does that mean? It means that solutions of this system and solutions of the original system are one and the same. They're exactly the same. And that's the point. We're simplifying the system, so now we can read off the solutions very easily, hopefully. Okay, so let me translate this now back into a system of linear equations in the original variables, which were x1, x2, and x3. So the system of equations that corresponds to this, if we read the top row, 1, 0, minus 5, 1, that corresponds to x1 minus 5x3 equals 1. And the second equation is x2 plus 2x3 equals 0. And the third equation we're not even going to write down because it's 0 equals 0. So it's no use to us at all. Now we have 2 equations in 3 variables. How are we going to solve this? We're going to look at the non-leading column on the left-hand side. So this is the non-leading column. That is going to correspond to a parameter. It means that there's a one-parameter family of solutions to this system. And it's the existence of this non-leading column on the left-hand side that's going to tell us this. And let's see why that is. Because if we look at these 2 equations, we say, okay, if we look at these 2 equations, we see that, okay, x1 minus 5x3 equals 1, x2 plus 2x3 equals 0. There's a degree of freedom. Like we could let x3 be anything we wanted to. And then x1 is going to be determined in terms of that. And x2 is going to be determined in terms of that. That's exactly what we're going to do. We're thinking about this third variable, which corresponds to the third column or the non-leading column, as being free. It's unconstrained. It can be anything it wants. So we're going to let x3 be a parameter. Okay, lambda we often use. Okay, that's a parameter. Then we can see that x1, if we solve for that, We'll bring the 5x3 on the other side, so we get 5 lambda, 1 plus 5 lambda. x2, we solve for that, we get minus 2 lambda. And x3 itself is just lambda, we said. What we have here is a solution to the original system. We could also write it as vector x1, x2, x3 is 1 plus 5 lambda minus 2 lambda, lambda. And if we separate that out, we could actually write it as 1, 0, 0, that's the stuff not involving lambda, plus lambda times the vector 5 minus 2, 1. So what is that? In terms of a diagram, there's x1, and there's x2, and there's x3, maybe there's 1, there's 1, there's 1. Then 1, 0, 0, that's that point there. So it's a line that passes through that point. And a direction vector for it. We have to go 5 in this direction, minus 2 in this direction, and 1 in this direction. So that's a total of 5, and then over here, and then up here. So maybe something like that. Right? So this would be the vector. That's the vector 5 minus 2, 1. And so the line that we're describing is the line that goes through this point, 1, 0, 0, which is parallel to that direction vector. In other words, it's going the same direction, so we'll draw it parallel like that. So it's a line in three-dimensional space, in 3D, through the point 1, 0, 0, with direction vector 5 minus 2, 1. So this illustrates really the entire story, in some sense, of taking an original system that we started with, writing down the augmented matrix for it, right here, that's the augmented matrix for it, and then row reducing it, first of all to get to this row echelon form, which is the situation where the leading entries of the rows are ones. That is, the leftmost entry in every row, which is non-zero, is actually 1. And everything below those leading entries is 0. And then we sort of proceed more and sort of eliminate everything above those leading entries until we get this fully reduced row echelon form where there's zeros entirely in the leading columns except for the actual leading entries themselves, which are 1s. And the row of zeros, if there are any, are at the bottom. And from that, we were able to pretty easily write down the corresponding new system of equations and basically solve it by introducing a parameter for the non-leading column. In this case, there was one non-leading column, so there was only one parameter. If there are more than one non-leading columns, then there will be more than one parameter. Okay, so and finally we end up with, in this case, a unbounded number of solutions. The solution set is a line, geometrically corresponding to the situation. We have these 3 planes, and they 2 of them meet like this, and then the third one is like that too. So they all meet on this common line. Okay, so that's great. So please make sure that you understand all those steps, and next time we'll sort of be a little bit more abstract and sort of clarify what exactly the sort of official algorithm is, but it's all kind of contained in this one example. So if you understand this example, you have a good basis for understanding row reduction and Gaussian elimination.